Understanding Time, From Mystery to Clarity. The Change-Driven Reality of Time. August 2025. By Dr. Syed. In loving memory of my sister Shaima, whose fleeting time among us was too short to truly behold the world or fulfill the promise she carried. My first encounter with the intricacy of time. My eldest sibling, Shaima, died at the age of 9 in a tragic accident. She was severely burned by boiling water. I was only 4 or 5 years old at the time, and it was an experience of profound trauma and shock, a raw and brutal confrontation with life, in its most unforgiving and unsympathetic face. When her lifeless body was brought home from hospital, I was filled with a haunting curiosity. Why wasn't she moving? What was death? What had happened to that part of Shaima who would always respond to my questions and childish provocations? Where had it gone? Would it return? When? That devastating moment marked my first encounter with deep, existential questions and emotional awakening to the fragility of life and the unsettling mystery of death. It was then that I first grasped, however dimly, the possibility of my own mortality, and with it, the overwhelming idea of eternity that is a never-ending period of time, stretching into infinity. I was told by the elders that Shaima had died, and she would never, ever return to this world again. Instead, it was we who, sooner or later, would leave this world to join her on her eternal journey. I would grapple silently with the idea of a never-ending stretch of time, trying to comprehend what eternity truly meant. I began thinking about my own mortality, about the inevitability of death, and it was extremely difficult to imagine my own demise. I would ask myself, if I die for how long? Is it really true that I would never return to this world again? Never ever? I couldn't bring myself to accept the idea of total annihilation, of ceasing to exist forever and ever. The thought, though deeply disturbing and unsettling, was at the same time strangely captivating. It was both terrifying and fascinating to contemplate something so profound and unknowable. If Shaima was not to return in the future, could we perhaps go back in time to relive the moments when she was alive in the past? This seemed to be a much trickier question. Many people, both ordinary and highly learned, did not entirely reject the possibility of time travel, especially to the past. This notion captivated my imagination, and I began to daydream about traveling back in time to re-experience the warm, early childhood memories when Shaima was still with us. Given my nostalgic and inquisitive nature, my curiosity extended even further. I became deeply fascinated with the idea of journeying to the distant past, such as 100 years ago, to live alongside my 4 grandparents and share, in the rhythms of their daily lives, seeing how they lived, what they valued, and how the world felt through their eyes. Getting deeper into the notion of time. When I grew older and entered my teenage years, I started reflecting more deeply on smaller and smaller periods of time. I realized that one could never really reach at the smallest unit of time, because any duration could always be divided in half, and then that half into another half, and so on infinitely. Mathematics taught me that time is a continuous variable, meaning it can be divided endlessly, that is to half, half of half, half of half of half, ad infinitum, which is a product of rational, abstract thinking. This stands in contrast to discrete variables, like the number of children in a family, where you can't have half a child in any meaningful sense. This continuous nature of time fascinated me deeply. It filled my thoughts with curiosity about what might occur during those incredibly tiny slivers of time. What did such fleeting instants actually mean? What kind of events could possibly happen during them? What kinds of creatures could perceive such minuscule intervals? What kinds of instruments could measure them? The clock in our house could measure seconds as the smallest unit of time, and even thinking about 1/10 of a second already felt challenging. So then, what would a millionth of a second mean, or even a billionth of a second? it became clear that for most everyday experiences, humans cannot detect or process events shorter than about 20 to 30 milliseconds without the help of specialized tools. Yet as fascinating as these thoughts were, they also unsettled me. I began to suspect that something might be flawed in this way of thinking, that is, viewing time as endlessly divisible, as something purely abstract and independent of matter or change, might be missing something essential. In the real world, surely there must be a limit, a smallest measurable unit of time. It couldn't go on forever, getting smaller and smaller. There had to be a boundary, a fundamental limit, what mathematicians might call the smallest infinitesimal unit. The proper description of time remains a key unsolved problem in science. In classical physics, time is an absolute backdrop against which events unfold, independent of the observer or the events themselves. Isaac Newton conceived of time as absolute and universal, which flows equably without relation to anything external. Even in common knowledge or collective understanding, time is considered as something independent which is responsible for eroding and degrading of things, as Leo Tolstoy, the renowned Russian writer and thinker, in his famous book, War and Peace, wrote, "Time erodes everything." I was no exception. Like rest of the people, I was of the opinion that time existed independent of other material realities and it was flowing like a stream of water. But again, it was extremely difficult to fully appreciate this mysterious invisible flow. What exactly it was? How was it flowing? What was this duration? With what speed? Posing the simple question, how fast does time pass, exposed the absurdity of the very idea. So, time seemed to be unbelievably elusive and ineffable, and it was practically impossible to grasp it logically. Again, this was very disturbing and frustrating to fail to grasp such an ordinary and mundane everyday experience. Time also seemed to be a deeply psychological entity, therefore, decorticating it objectively seemed to be almost an impossible task. Finally, I decided to give up and stop thinking about it altogether. However, my friend and intellectual buddy, Dr. Bashir Hamid, became obsessed with the idea of time. He would regularly steer our discussions toward the question of the nature of time. We both were deeply inspired by the writings of Allama Iqbal, who, in turn, was influenced by the philosophy of Henri Bergson regarding time, such as the concept of pure duration and élan vital. Through persistence, Dr. Bashir succeeded in reigniting my old passion on this topic. We would discuss, among many topics, the philosophy of time at length during long evening walks and talks. Over time, our views on the nature of time began to diverge. Dr. Bashir upheld the classical view of time as an independent and fundamental reality. He even glorified it further by adding extra dimensions to time, in an attempt to explain complex philosophical and scientific puzzles. For me, however, time became demoted to a position of secondary importance in the architecture of the universe. I became convinced that time was subordinate to matter and change, a second-order reality rather than the foundational one that classical perspectives had maintained. These contrasting viewpoints enriched our discussions and deepened my exploration of this endlessly fascinating concept. Over time, I realized that it was worth investing my energy into exploring the nature of time, with the aim of making this elusive concept more accessible and understandable. In other words, I came to see my mission as an effort to tame this wild entity, a phenomenon that defies simple explanation and resists rational containment. At the same time, I felt compelled to address some widespread misconceptions about time that often go unchallenged. As I delved deeper into the subject, it became clear that even classifying different existing perspectives regarding time was far from straightforward. For instance, despite their apparent differences, I came to believe that Newton, Einstein, and even Immanuel Kant all ultimately fell into the same conceptual category regarding time. They each treated it as a kind of universal backdrop, something that exists independently, a canvas upon which events unfold, regardless of whether matter and change is present. There are currently two major philosophical perspectives on the nature of time, called the A theory and the B theory. The A theory views time as a dynamic process, with a constantly changing present moment, emphasizing the distinct and evolving nature of the past, present, and future. In contrast, the B theory conceives time as a fixed, four-dimensional block in which all moments, past, present, and future exist equally and simultaneously. Interestingly, both A and B theories regard time as a fundamental and independent entity. In doing so, they overlook an alternative possibility, that time might instead be a relational measure of other fundamental realities, such as matter and change, rather than a standalone entity. Therefore, none of these celebrated thinkers or the proposed theories radically questioned the prevailing notion of time as a continuous, autonomous flow. Instead, they each integrated this idea into their respective frameworks. For Newton, time is an absolute, mysterious flow, universal, fundamental, and irreducible to anything else. Einstein transformed time into the fourth dimension of space, giving rise to the concept of spacetime, where time was treated as being just as fundamental as space itself. For Kant, time was an a priori form of intuition, a necessary and universal condition for human experience, abstract and subjective, yet indispensable and irreducible to other categories of understanding. What they all seemed to share, in my view, was the belief in the irreducibility of time, that is, its status as a foundational element that could not be broken down into or explained by more basic constituents. This write-up proposes a fundamentally different explanation of time, one that diverges from traditional views by suggesting that time is not a fundamental reality but is instead reducible to more basic elements such as matter, energy, and the change or motion occurring within space. In other words, time as a parameter is not indispensable in physical equations. Consider a simple example, the calculation of speed, typically expressed as distance traveled divided by time. If a trip from Washington, D.C. to New York City covers 362 kilometers in 4 hours, the average speed is 90.5 kilometers per hour. However, since an hour is simply 1/24th of a full rotation of the planet Earth around its axis, we could just as easily say that in every 1/24th of Earth's rotation, 90.5 kilometers were traveled. Here, time is replaced by its definition in terms of Earth's rotation, demonstrating that the concept of time as an abstract entity is unnecessary, though the substitution may be cumbersome, that is, replacing the single word, that is to say an hour, with the phrase 1/24th of one full rotation of the Earth around its axis. This simple example illustrates how motion and change can be described without invoking time as a separate, mysterious parameter. How could a non-professional write on such a complex topic? The reader may understandably ask, how can I, a layperson with no formal training as a professional physicist or philosopher, venture to write about such an intricate and profound subject as the nature of time? The following are some of the motives I can think of that inspired me to explore and write on this topic. First and foremost, the intended audience for this writing is not a group of experts but other curious minds. It is aimed at a general readership as an average person with a basic level of education and some levels of curiosity. I believe that many of the brilliant minds and world-class experts in physics, philosophy, and metaphysics have not given sufficient focused attention to this topic, perhaps for the following reasons. They had too many demands on their time and attention, leaving little room to contemplate the nature of time from a common person's perspective. They may have readily accepted the prevailing notion of time without questioning it deeply or treating it as a problem worth revisiting. They might have viewed time as too elementary a concept unworthy of further scrutiny. They might have been unable to fully detach from the psychological dimensions of time, which limited their ability to consider its nature with complete objectivity. Considering all this, I felt there was a meaningful opportunity for me to contribute to an idea that is both universally important and deeply familiar, yet strangely underexplored. Writing on this subject felt like a chance to fulfill a childhood dream and a promise to myself, to explain something in this world that no one, despite millennia of human thought, seems to have clearly understood. Despite the thousands of thinkers, philosophers, and physicists who have walked on Earth and written extensively, the concept of time remains an enigma, still waiting to be seen from a truly fresh and independent perspective. The literature seems to be surprisingly poor regarding nature of time. To my surprise, the literature about the nature of time was not rich enough or easily accessible. For example, there isn't many books on the nature of time when I am searching online. With a lot of effort, I could only find one book on the nature of time and another one on the philosophy of time from a total of 12 million books available in the library of Oxford University, which I happened to visit during my travel to the university in December 2023. In addition, many of the literature that I have come across don't really address the question of the nature of time per se. They rather deal with the properties and attributions of time. For example, modern physics has really focused on the relativistic character of time without touching the nature of time itself, that is, what is it that is relative? It is surprising to note that the celebrated philosopher Immanuel Kant has completely avoided the question of the nature of time while philosophizing on the notion of time. He has simply accepted the prevailing naive explanation of the notion of time as a universal flow, as had been popularized by Isaac Newton. Kant has just put that populistic view of time into his philosophical system. For him, time becomes subjective as a component of human intellect and together with space serves as a precondition, or a formal condition, as he puts it, for making sense of the outside world. According to Kant, our mind imposes time on the world. And so there is no such thing as time outside of our minds. For Kant, time is a form of intuition, a framework through which the human mind organizes sensory experiences. It seems that scholars have largely given up on the project of explaining the nature or essence of time. Many scholars, including Bertrand Russell, believe that a rigorous definition of time is an impossible task, arguing that any attempt inevitably results in a circular explanation. In other words, definitions of time often end up relying on the very concept they are trying to define. For example, saying time is what measures the passage of events is circular because it presumes the existence of time, as passage, to explain what time is. It does not offer an understanding of time that stands independently of the notion of passage or flow. However, through my common sense approach, I believe I have succeeded in arriving at a non-circular definition of time. The central ambition of this writing is to demonstrate that such a definition is not only possible but also clear and accessible. My approach is grounded, objective, and concrete. I believe I have managed to set aside my emotional or psychological attachments to time while investigating its nature. In other words, I have been, if I may put it bluntly, cruelly objective in my dissection of the concept of time. Aristotle's view on time and its shortcomings. Aristotle, over 2 millennia ago, arrived at a conclusion that closely resembles the common sense view of time. In his book called Physics, Book 4, he defined time as the number of changes with respect to before and after. While this definition is insightful and has influenced thought for centuries, it is not without problems. It relies on inherently temporal terms, before and after, which makes it circular. It assumes the very concept of time in order to define time. In my view, Aristotle's understanding lacked the explicit clarity needed to truly demystify the concept. A more precise approach is to regard time as a human construct used to measure or quantify change in motion. This perspective should not be confused with Kantian idealism, where time is seen as a framework imposed by the human mind to organize sensory experiences. My approach avoids both circular reasoning and subjectivism, grounding the concept of time firmly in observable, physical phenomena. Search for an everyday life experience to understanding nature of time. I am not a physicist, although it was a teenage dream of mine to become a nuclear physicist. Nor am I a philosopher, though exploring philosophical ideas have been the joy of my life. Neither am I a metaphysicist, though abstract ideas and entities, such as some mathematical equations, are among the most beautiful things I know of in this world. One might then ask why I am writing about such a deeply physical, philosophical, and metaphysical subject, while I am not an expert in any of these fields. I must say that I am not writing as an expert and do not intend to address the nature of time from a physicist or philosopher's perspective. My goal is to demystify the concept of time through a common-sense approach or everyday life experiences, as a layman armed with nothing more than a modest grasp of general science and simple and common experiences. I will touch on modern physics and philosophical concepts only to the extent that they remain accessible to the average literate reader. I want to demonstrate that one can form a better understanding of time without resorting to technical jargon or advanced knowledge of physics, philosophy, or metaphysics. My ambition is to show that there is nothing inherently mysterious about time. It is grounded in everyday physical phenomena. There is no such thing as an independent flow of time, separate from matter, energy, change, or motion. I also aim to explore and clarify some of the conceptual difficulties surrounding time. For instance, does time have a direction? Is time travel possible? How does the nature of time relate to the second law of thermodynamics or entropy? Finally, I hope to examine the linguistic challenges that often cloud our thinking about time. Time is, in many ways, a basic concept, one that everyone seems to understand intuitively, yet no one can fully explain it rationally. We speak of time in terms of duration, past, present, and future. But ask people to define what time actually is, and most will struggle, echoing St. Augustine's famous reflection, "If no one asks me, I know. If I wish to explain, I do not know." With my very limited and amateur understanding of modern science, particularly quantum physics and the theory of relativity, I attempted to examine the nature of time through those lenses, only to be disappointed. Understanding these scientific theories is already a daunting challenge for a non-expert, and combining their complexity with the elusive nature of time makes the task nearly impossible. Moreover, in both relativity and quantum physics, time is treated more as a parameter used to balance equations than as a phenomenon to be deeply understood. These theories do not really tackle the nature of time. They were developed within a cultural context that already presumed time to be a universal, independent flow. This realization convinced me that one need not turn to highly complex modern science to understand time. Humanity has had an intuitive grasp of time since the earliest days of civilization, long before the modern physics or advanced mathematics existed. In fact, those sciences emerged from time-related ideas that had already been understood for millennia. Early humans observed natural rhythms such as the sun's position to measure time. Ancient civilizations measured shadows to track time and developed the first clocks. Based on this history, I concluded that the best way to understand time is through a common-sense approach, one that is rooted in ordinary everyday observation and simple reasoning, without the need for elaborate theories or advanced laboratories. Interestingly, my own first experience of tracking time was when I started the first year of school. I observed the sun's rays reflecting on the wall of our classroom, which was in the basement of a building and had a small window facing south. I had marked specific spots on the wall where the arrival of the sun's rays would correspond to recess time and the spot where they indicated school dismissal time. I remember sharing this discovery with my mom. She explained to me that as the seasons moved towards fall and winter, the sun's rays would slowly penetrate deeper into the classroom, and so I would have to revise my tracking spots accordingly. Time is not fundamental, its relation to matter and motion. The controversy about the nature of time could be as old as the dawn of human civilization. For example, in 5th century BCE Greece, Antiphon, the sophist, in a fragment preserved from his chief work on truth, stated, "Time is not a reality, or hypostasis, but a concept, or noma, or a measure, or metron." This raises a critical question often debated in the literature: is time real? However, I think this question is vague because the term real itself is ambiguous. A better question, I would say, would be to ask whether time is a fundamental reality. In other words, is it independent of other fundamental realities such as matter, energy, change, and motion? My answer is straightforward. Time is not fundamental. We cannot meaningfully talk about time in the absence of matter and change. In a sense, we could say that time is emergent, meaning it arises from matter as it undergoes change. But even that is not sufficient. In addition to the existence of matter and change, there must also be a conscious being capable of perceiving and ordering those changes into discernible events. Time can be fully explained in terms of matter and motion, or energy and change. It is simply a way of describing these phenomena. To me, matter and motion are the true fundamental realities, intertwined like two sides of the same coin. Matter exists as the fabric of reality, and it is in constant state of flux, from the largest celestial bodies to the smallest subatomic particles such as electrons and quarks. Time, then, is nothing more than the measurement of change or motion, a means to order events resulting from this continuous transformation. Timekeeping, key to understanding the nature of time. In fact, our notion of time is very much related to the motions of planet Earth, both rotation and revolution. Rotation is the movement of the Earth around its axis, which creates day and night and has been divided into 24 segments or hours. Each hour represents 1/24th of a full rotation. Revolution is the movement of the Earth around the Sun in a fixed path or orbit, which creates different seasons within a year and has been divided into 12 months and each month into 30 or 31 days except for February. Then the hours have been divided into minutes and minutes into seconds and so on. Therefore, each one of these units of time are traceable back to the motions of Earth. The division of the day into 24 hours and the year into 12 months, among other time measurements, predates the modern heliocentric understanding of the Earth's movements. In ancient times, it was commonly believed that the Sun revolved around the Earth, with a changing incidence angle throughout the year causing the alternation of seasons. This geocentric view shaped early timekeeping systems, which were based on the Sun's apparent movement across the sky rather than on the Earth's orbit around the Sun. Time as a metric for change and motion. Time is a human construct, much like metrics for weight or length, designed to measure change or motion. It is not a fundamental structure of reality, not a dimension independent of matter and change. Instead, it is a tool for understanding and sequencing events. By sequencing, I mean ordering events through a nominal arrangement system, using ordinal numbers such as first, second, third, etc., to organize events relative to one another in space. For example, an hour is not a measure of some abstract flow or pure duration. Instead, as I mentioned earlier, it is a measure of change, specifically 1/24th of Earth's rotation on its axis. This comparison with a reference standard change, that is the Earth's rotation, forms the basis of time measurement. Unlike metrics such as weight and length, which measure static entities, time measures dynamic phenomena. This very dynamism lies at the heart of its elusiveness and the difficulty we face in comprehending it intellectually. Change and chain of events. Motion or change are inescapable realities of the material world. We can think of the following three kinds of changes. 1. Change in location, or motion. This refers to physical displacement of an object relative to other objects in space, often on a macro level, presupposes real and objective space which allows displacement of objects. Motion is a subset of change, specifically referring to positional shifts. For example, a ball rolling down a hill or the Earth rotating around its axis. 2. Change in quality. Change in quality refers to the displacement or transformation of the constituting particles of an object, often occurring at the micro level, such as molecular transformations or a chemical change. This type of change can be subtle yet significant. For example, when iron reacts with oxygen and water, it transforms into iron oxide with the chemical name of Fe2O3NH2O, a process commonly known as rusting, or when ice melts into water, which is a change of state, or when a metal rod heats up, which is a change in temperature. The aging process in living organisms, including humans, is also part of this category, marked by continuous micro-level displacements and molecular transformations within our body cells. From this, it follows that we are entirely immersed in, and inseparable from, the all-encompassing process of change, making it impossible to assume a purely detached observer's position. 3. Change in substance. With a common-sense approach, change in substance is difficult to imagine. Even though modern physics suggests change in substances, such as in the example of pair production, that is the transformation of matter into energy, but in a deeper level, where we cannot distinguish matter and energy, the substance cannot change. Can it be fields, strings, or some other entity? At the quantum level, particles are excitements of underlying energy fields. The distinction between particles and waves, matter and energy, becomes blurred. Everything is better described as fields that interact. This is linked with the idea of conservation of energy and matter as described by Einstein's famous equation, E=mc². Events are the outcomes or observable points where motion and change are recognized. They tie motion and change of matter into a framework we can analyze, measure, and understand in space, relative to other events. Without motion or change, events would not exist, as there would be no transformations to observe or record. For example, the ringing of an alarm clock is an event resulting from the motion of internal clockwork and the change in state, from silence to noise. Time is the measurement of change, motion, and the ordering of events in space. As discussed earlier, the nature of time can be understood through the motion and transformation of matter and energy, which give rise to events. Time, in this sense, serves as a conceptual tool that allows us to organize and make sense of these events, rather than being a fundamental reality in itself. Unlike matter and change, which are irreducible and foundational aspects of existence, time emerges from our perception of change and our need to measure it. The rotation and revolution of the Earth, producing the alternation of day and night as well as the cyclical progression of seasons and years, played a key role in how our ancestors first conceptualized and measured time. The notion of time is indeed very difficult to grasp. That is due to 1. Universality of change. The universality of time is related to the interconnectedness of all the matter and energy in the entire universe. All the motions and changes in the universe from the smallest to the biggest are interconnected and constantly influencing each other despite millions of light-year distances. Therefore, any motion and change anywhere in the universe are the results of the effects of total matter and energy in the entire universe. Considering time as the measurement of change and motion, it also becomes universal. All the matter in the cosmos is interconnected and is interacting with each other, reminding us that every change is part of a much larger story. Like the idea of butterfly effect, the changes in the remotest regions of the universe, for example the remotest galaxies, could affect the events here on the planet Earth and vice versa. we do not have isolated events or isolated regions in the universe. Therefore, all events in the universe are fundamentally interconnected. Based on the modern physics, the gravity is a universal phenomenon which can influence over vast distances across the universe, billions of light years. Similarly, the quantum entanglement and quantum field seems to connect the matter across the universe, regardless of unimaginable vast distances, which could be billions of light years. 2. Omnipresence of change. We as human beings who want to measure changes are ourselves part of change, as an omnipresent process. So, we cannot be simply observers of the events happening around us, we are always participants in the change process as well as in its measurement. 3. The dynamic nature of change. Normally we find it easy to deal with the static phenomenon to measure. Note that at the micro level, nothing is static, but change is dynamic, hence much difficult to measure and understand. 4. Another layer of complexity in understanding the measurement of change is the fact that it can only be measured in comparison with another change, so not only time is measuring something dynamic, it also adds the complexity of relativity or proportionality of the measurement of two dynamic processes. The human mind often has difficulties in grasping proportional phenomenon. As Bertrand Russell has observed, the idea of a relational proposition seems to have puzzled most of the great philosophers from Plato down to Hegel. 5. The different categorization of time such as flow of time, serial time, measurement of time, pure duration, etc., while all in reality are the same, have added to the confusion and difficulties in terms of fully grasping the nature of time. The complexities inherent in understanding time stem from a myriad of factors, both physical and emotional. Our language, often imprecise and misleading, further complicates our grasp of time's true nature. Physically, the challenge lies in numerous interrelated motions and changes, making accurate comprehension difficult. Thus, our understanding of time is shrouded in confusion, with added layers of emotional attachment and linguistic ambiguity, rendering the true essence of time elusive and multifaceted. Our measurement of time, whether by ordinary people or sophisticated scientists, is fundamentally based on the rotational and revolutionary movements of the Earth. We refer to 24 hours as one full rotation of the Earth on its axis and a year as one full revolution of the Earth orbiting the Sun. These units are further subdivided for more precision. An hour is 1/24th of a full rotation of the Earth on its axis, a minute is 1/1440th of a full rotation, and a second is 1/86,400th of a full rotation. A rigorous definition of time, through change or motion, requires avoiding the usage of the concept of passage or flow of time, while we speak about the division of the rotation of the Earth on its axis into smaller units. Consider an Earth globe rotating on its axis. One complete rotation can be called 24 hours. Consider a viewer who is looking at the rotating Earth globe through a slit. Draw a red line on the globe which is connecting the north to south poles. As the globe rotates around its axis, the red line appears to the viewer through the slit, and as soon as he sees the red line again through the window, an event happens that is 24 hours have passed. We use the terms past, not to mean that something flowing has passed, but to give a name to the event, a complete rotation of the Earth globe on its axis. We will come back to the tricky challenges leading to confusions due to language. Now draw 24 red lines with equal distances linking north and south poles. Now, each time the viewer sees a subsequent red line, he marks an hour. This process can be continued for the smaller units of the rotational movement of the globe. This way of measuring the rotation of the Earth, which is dividing one complete cycle of day and night into 24 hours, dates to antiquity, which may be traced back to 1550 BCE to the Egyptian civilization. Understanding the concept of time using Earth's movements is relatively straightforward. However, measuring other motions and changes, or the sequence of events, is more complex. Properly understanding them requires comparing them with a familiar motion or change, such as the rotation or revolution of the Earth. Therefore, Earth's rotation or revolution serves as a standard measurement unit of reference to categorize and order other events. For instance, traveling from one location to another might take a quarter of a full day and night, which is described as 6 hours, 24 divided by 4. Similarly, a child's first words might be marked after 2 complete revolutions of the Earth, or the return of the seasons to their starting points, which is described as 2 years. Time and speed, an example of reducing time to motion. The relationship between time and speed is complex and often misunderstood. Traditionally, speed is defined as the distance traveled divided by the time taken. This definition assumes a consistent flow of time, an independent measure against which motion is gauged. Reframing the definition of speed, however, a closer analysis suggests that speed fundamentally involves comparing one motion, such as an object's movement, against the segment of Earth rotation that defines an hour. Example: when we say a car travels at 100 kilometers per hour, we compare the car's distance traveled to 1/24th rotation of the Earth. Earth's rotation, as a rhythmic and harmonious motion, serves as a reference standard for the measurement of time and, consequently, serves as the basis of calculation of speed of other motions or changes. We measure the rate of other changes or motions relative to this universal reference, that is Earth's rotation. If we consider 2 rotating globe balls, speed, therefore, is the relative appearance of successive color bonds on each globe. Consider the following scenario. 2 rotating globes. Imagine 2 identical globes rotating on their axes. Color differentiation. One globe has a red line connecting the poles, while the other has a blue line. Speed difference. The blue globe rotates twice as fast as the red globe. Observation. Relative appearances. An observer viewing both globes through a narrow slit will see the red and blue lines appear and disappear periodically. Frequency of appearance. Due to the difference in rotation speeds, the blue line will appear twice as frequently as the red line. With this example, we notice that for explaining speed, referring to time is not indispensable. This scenario demonstrates that speed can be understood as the relative frequency of appearances of a marker on a rotating or moving object. Regularity versus harmony. One might object in using the rotation and revolution of the planet Earth as the basis of our understanding of time. How can we be sure that these movements are indeed regular, that is, they are uniform and not accelerating or decelerating randomly? It may be that the Earth's motions are irregular or even chaotic, and we may not have any means to ascertain that, unless accepting the flow of time as a solid reference point at the background of all events. This objection is deep and insightful. With regards to the movements of the Earth, in my opinion, instead of the notion of regularity, we better use the notion of harmony. First, the rotation and revolution of the Earth are harmonious, or proportional, and rhythmic, or cyclic, that is, they have a constant proportion. For example, 365.24 rotations of the Earth round its axis, which we call 365.24 days, match precisely one orbit around the Sun, which we call a year. This proportion is constant, and it does not change from year to year, hence Earth's motions are both rhythmic and harmonic. These rhythmic motions are in harmony with those of other celestial bodies, such as the revolution of the Moon around the Earth and the orbits of planets around the Sun. While the Earth's rotation may be regular, irregular, or even chaotic, what matters is that its movements align harmoniously with those of other celestial objects. Even if these motions appear irregular or unpredictable, they maintain fixed proportions within their respective rhythms. This interconnectedness of the motions of celestial bodies, which also extends to other natural phenomena, suggests an underlying harmony or a natural order woven through the cosmos. From this discussion, it follows that time understood as the measurement of motion relative to a reference motion, such as the Earth's rotation or revolution, is inherently scale-free. As long as the proportions among various motions remain constant, including physiological processes within our bodies, we cannot objectively determine whether these proportions have radically shifted relative to similar motions elsewhere in the universe. This idea echoes the implications of general relativity, particularly the phenomenon of time dilation observed when an object approaches the speed of light or is situated near a strong gravitational field. In such scenarios, time dilation is relative to the observer. While an external observer perceives time slowing down for the spaceship, those within it experience time normally. Simultaneously, the scale-free nature of time as a measure of motion resonates with certain mystical perspectives, such as Allama Iqbal's notion of the supereternal now, where time is not a linear sequence but a unified, transcendent experience, suggesting that what is merely a moment for one observer could encompass an entire eternity for another. Interestingly, many natural processes follow rhythmic patterns with fixed proportions, allowing them to serve as reliable timekeeping mechanisms. Beyond celestial motions, an example is radioactive decay, which is measured by the half-life of elements. For instance, plutonium-241 has a half-life of approximately 14.4 years, meaning that after each 14.4 years, half of a given sample will have decayed. This proportional relationship between natural rhythms underscores the deep interconnectedness of cosmic and atomic timekeeping. Therefore, whatever the nature of the Earth rotation and revolution, given that it agrees with the movement of other heavenly bodies proportionally, it can be called regular. So, it follows that the definition of regularity of movements of the Earth boils down to its proportionality or harmony with the movement of other heavenly bodies. As such, the rotation and revolution of the Earth becomes a reference point, and all other movements and changes are compared with it, which is called time, and the resulting figure is called the speed of change or motion. For example, we say the Moon completes, on average, its full revolution around the Earth in 27.5 days. This means that the 27.5 rotations of the Earth correspond to one complete cycle of the revolution of the Moon around the Earth, which is the lunar orbit. We consider the rotation and revolution of the Earth as regular, and hence any departure of any other movement or change from it is considered irregular or chaotic. This shifts the focus from a subjective, fixed time flow to a more dynamic, interconnected understanding of time as a relational phenomenon. Apart from orbital motions, fundamental level changes, whether through atomic, subatomic, radioactive, or photon-based transitions, are all rhythmic and harmonious, and therefore can be used as clocks. These changes provide incredibly precise, predictable measurements of time, making them invaluable tools in both everyday applications, like GPS, and cutting-edge science, such as quantum computing and astronomy. The implications of lack of natural harmony. The absence of cosmic or universal harmony, as I elaborated upon in the preceding paragraph, would not only pose serious challenges for timekeeping but could also result in a complete derangement of the very concept of time as we know it. Imagine a world where events unfold in a non-harmonious fashion, like in dreams, where we are unable to discern constant proportions between different motions. In such a scenario, it would be impossible to create any reliable clocks, whether artificial ones made by humans or those derived from natural phenomena, and hence, any departure of any other movement or change from it is considered irregular or chaotic. This shifts the focus from an objective, fixed time flow to a more dynamic, interconnected understanding of time as a relational phenomenon. Apart from orbital motions, fundamental level changes, whether through atomic, subatomic, radioactive, or photon-based transitions, are all rhythmic and harmonious, and therefore can be used as clocks. These changes provide incredibly precise. We consider the rotation and revolution of the Earth as regular, and hence any departure of any other movement. We consider the rotation and revolution of the Earth as regular, and hence any departure of any other movement or change from it is considered irregular or chaotic. This shifts the focus from a subjective, fixed time flow to a more dynamic, interconnected understanding of time as a relational phenomenon. Apart from orbital motions, fundamental level changes, whether through atomic, subatomic, radioactive, or photon-based transitions, are all rhythmic and harmonious, and therefore can be used as clocks. These changes provide incredibly precise, predictable measurements of time, making them invaluable tools in both everyday applications, like GPS, and cutting-edge science, such as quantum computing and astronomy. The implications of lack of natural harmony. The absence of cosmic or universal harmony, as I elaborated upon in the preceding paragraph, would not only pose serious challenges for timekeeping but could also result in a complete derangement of the very concept of time as we know it. Imagine a world where events unfold in a non-harmonious fashion, like in dreams, where we are unable to discern constant proportions between different motions. In such a scenario, it would be impossible to create any reliable clocks, whether artificial ones made by humans or those derived from natural phenomena, because the fundamental principle of timekeeping, whether through mechanical devices or celestial cycles, relies on harmony between different movements. These movements must repeat in a predictable, constant manner. As discussed earlier, time perception is tied to our memories, which are shaped by the smooth, continuous flow of events. In a world devoid of harmony, our memories would be severely disrupted, leading to a fractured understanding of time. We would no longer experience time in the cohesive manner we do now, as the flow of events would be erratic and incomprehensible. The concept of timekeeping, which many view as mundane, everyday task, is often seen as separate from the deeper, more mysterious nature of time as a homogeneous, flowing essence. However, in reality, timekeeping is central to our understanding of the very nature of time itself. If we fail to maintain accurate and predictable timekeeping, one that depends on the natural harmony between the various motions in the universe, we risk unraveling the very notion of time as conceived by thinkers like Newton. In this view, the essence of time is inseparable from the process of timekeeping, which is, in turn, rooted in the cosmic harmony that governs natural phenomena. Thus, the true nature of time fundamentally depends on the universal harmony of movements and events in the world around us. Therefore, we recognize that the time is not just measured but made possible by the grand universal symphony. The universality of time as the measurement of change. Time's universality stems from the universality of motion and change in matter and energy. The human difficulty in grasping the concept of change at a fundamental level, especially at microscopic or atomic scales, further complicates our understanding of time. Unlike static quantities like weight or length, change is dynamic and continuous, making it harder to reduce into simple, static pieces for intellectual comprehension. Additionally, we humans are ourselves participants in the process of change. We are not mere observers of change around us. Meaning that we are not only sensing the perception of time, via changes and movements in the environment, but also through introspection, that is sensing the changes happening inside our bodies. Our bodies and minds are in constant flux, our hearts beats each moment, blood flows through our blood vessels, neurons conduct impulses, metabolism occurs in every cell, and our psychological states shift continuously. This inseparable participation in the change process reinforces the illusion of time as an independent entity. The error in St. Augustine's argument against the change-driven reality of time. In the Confessions, St. Augustine argued against time as the measurement of motion by asking why time seems to pass even when things do not change or move. This objection can be addressed by recognizing that apparent stillness on the macro level does not mean a lack of change overall. Internally, all things, including seemingly static objects, undergo transformation at molecular or atomic levels. Furthermore, the Earth's rotation and orbital motion persist, and we ourselves are in constant physical and psychological flux. These changes can always be measured, even when specific macro-level objects appear stationary. Entropy and the arrow of time. The second law of thermodynamics is the only law in physics which has as a direction, meaning that it is not reversible, or we can say it is the only physical law which is not symmetric. As per the second law of thermodynamics, the entropy of a closed system, such as the entire universe, always goes up or stays the same, and it never decreases. In technical terms, the systems tend towards those macrostates which contain the highest number of indistinguishable microstates. As mentioned earlier, this argument is at the heart of the second law of thermodynamics. Some people have argued that the direction of the entropy, which is basically moving towards maximization, is a clue about the arrow of time. Although this is an exceedingly difficult and complicated subject and sounds quite convincing, I am of the view that even the changes or motions which do not follow any direction, unlike the second law of thermodynamics which is about maximization of entropy, can still be measured with time. Any change, whether with increasing entropy or decreasing entropy, if it results to discernible events, it can be measured with time, and the time would be always moving forward. Is there a notion of time at the microstate level? Our current understanding of time is entirely defined at the macrostate level, where changes or events are distinguishable from one another, making it easy to perceive and track differences between them. In thermodynamics and statistical mechanics, a macrostate refers to the large-scale, observable condition of a system, such as its temperature, pressure, or volume, while a microstate refers to the specific arrangement and behavior of individual particles, like atoms or molecules, that collectively make up that macrostate. At the microstate level, where gazillions of particles move in chaotic, random patterns, not only are the particles often indistinguishable from one another, but the overall configuration of the microstate itself can be nearly indistinguishable from each other. In such a scenario, the conventional notion of time becomes inapplicable. From this, we can conclude that change is essential for the concept of time. Yet for time to be meaningful, that change must produce discernible or distinguishable events. Moreover, a conscious observer, such as a human being, is required to perceive and order these events. It is this perception of sequence, one event following another, that gives rise to what is called the arrow of time. The conscious mind also compares and relates these ordered events, which allows for the measurement of time through relational changes. In a world of total chaos, filled with an infinite number of indistinguishable particles moving without recognizable patterns, the very notion of time, as we understand it, appears to break down. Thus, understanding time requires not only matter in motion but also meaningful changes that result in distinct events. Additionally, the existence of human consciousness is necessary to observe the arrangement of these events in a way that creates order with a specific direction, what we call the arrow of time. Language and the confusions about time. Words have a way of shaping not just how we talk but how we think, especially about abstract ideas like time or the soul. An important difficulty about understanding the nature of time is related to language. It seems that once we name something, it becomes an independent reality. Not only do we have a name for time, but we have also a name for the flow of time. For example, we say, "Time is flying," an expression that the time is moving very fast. Other similar examples that we could state are related to soul. Not sure what has been the real intention of our ancestors when they started referring to soul, but once the name was uttered, it became something real, an independent reality, and hence, so many theories to explaining it were proposed not only among common people, but also among top philosophers such as René Descartes, who popularized the idea of dualism of body and soul. Another example is the question of free will. Ludwig Wittgenstein believes that debates and confusion stemming from language are the results of what he calls the misuse of language and can be dissolved entirely. Interestingly, the problems arising from the misuse of language get further confused among consequent generations of thinkers. Generally, one would expect that over the course of history, things get clarified due to crowd wisdom and collective intelligence. However, for the problems arising from the misuse of language, such as time, soul, or free will, the understandings become even further blurred in the course of history. Why time seems independent. The illusion of time as an independent, flowing entity arises from the way we understand and measure other physical quantities. For example, mass, the unit of measurement for mass, e.g., kilograms, quantifies an object's heaviness or resistance to acceleration. Distance, the unit of measurement for distance, e.g., kilometers, quantifies an object's lengthiness or spatial extent. In both cases, the essence of the measured quantity aligns with the nature of the measuring unit. However, time measurement deviates from this pattern. Time units, e.g., seconds, hours, are not measuring a separate category whose essence is flowing or duration. Instead, they measure changes in motions, for example, the movement of the earth or the ticking of a clock relative to a chosen standard or reference motion or change. This confusion leads people to assume that time, like mass and length, must have an independent existence. However, this assumption fails because time measurement is fundamentally tied to change in motion, not to some independent, time substance. Flow of time. Dual perspectives on time. When referring to time, many people distinguish between two interrelated aspects, time as flow and time as measurement. This duality reflects the distinction between time as subjectively experienced and time as objectively measured. Time as flow, as Henri Bergson would say, is perceived as pure duration and independent, continuous reality that we live through. In contrast, time as measurement is a structured, quantitative representation captured through instruments like clocks and calendars, or natural phenomena such as the Earth's rotation and revolution. The concept of time as a mental construct often manifests as the sense of a universal flow of something, a perception that is deeply psychological and profoundly emotional, occupying a convenient place in our consciousness. Memory plays a crucial role in shaping this psychological experience, where the past and future are essentially reconstructions, remembering what was and anticipating what might be. St. Augustine emphasized that we experience time as a continuous flow within our awareness. For example, while listening to music, we mentally retain past notes, anticipate upcoming ones, and remain present with the current sound. This dynamic interplay of memory, attention, and expectation reveals how time, at its core, is a subjective phenomenon. Bertrand Russell captured this notion succinctly. The past, present, and future are basically remembering, considering, and expecting of events. Henri Bergson introduced the idea of pure duration to describe the subjective, qualitative experience of time as a continuous flow, distinct from measurable, or as he calls it, the spatialized time. Allama Iqbal, influenced by Bergson, embraced pure duration as an essential, spiritual aspect of reality, aligning it with dynamic creativity and the unfolding of life. Both thinkers regard pure duration as a fundamental reality, independent of motion or change, and as a precondition for any motion or change to occur. Many people think that if time stops flowing, nothing can move or change. In some way, they think that if the time stops flowing, everything in the universe will freeze, that is, no change or motion whatsoever would be possible, and no events could happen. This is indeed a remarkably interesting perspective and at the same time very strange thought. This way of thinking about time clearly reflects a Newtonian view of time. As mentioned earlier, the motion or movement is something gross, macroscopic, and visible, and so can be intermittent that it can stop. Change, however, is more subtle, universal, microscopic, and non-stoppable. The events created through microscopic changes can be slow to appear and therefore difficult to discern. For example, when the wind blows, the leaves dance in the air during the autumn is easy to see, which represents motions or movement. However, the deeper, molecular level changes and transformations in the leaves are much more subtle. It is those changes that transform the color of the leaves, for example, from green to yellow in autumn. While we can see the color change over the months, which is a slow process, we cannot see the underlying chemical or microphysical changes. The process of color transformation of the leaves is the results of a change process, which, though relatively slow, is continuous and is non-stoppable. As such, motion is observable and intermittent, but change is subtle, universal, and unstoppable. By distinguishing between the two, we can refine our understanding of time as a concept tied not just to visible events but to the continuous, underlying processes that drive the universe. If we link the understanding of time to motion or movement, we can easily find examples where nothing changes that is detectable by our senses, but the time still flows. This is exactly the false argument that led St. Augustine to reject the concept of time as the measurement of change. He failed to realize that the real change at the more subtle level, especially molecular, atomic, and subatomic levels, cannot stop at all. More importantly, the continuous changes in our own body, continuous beating of our hearts, flow of blood in our vessels, nerves impulses in our neurons, the process of metabolism in every cell of our bodies, cannot stop at all, which makes it practically a continuous change process. St. Augustine failed to introspectively recognize the changes occurring within his own body during the moment he perceived that nothing was moving or changing. Certainly, physiological processes in his body, heartbeat, breathing, neural activity, must have continued uninterrupted, otherwise, he would not have been alive to reflect on or report that period during which he believed nothing was changing. The consciousness itself, as William James has noted nicely, is the flow of a stream of thoughts, a change both inevitable and continuous for a conscious being, and cannot be stopped like a discrete process. It is this perpetual change in motion that is the hallmark of consciousness and time awareness of humans, which at the same time is an essential element of continuity of personal identity. Therefore, time is inseparable from change. It is not an independent flow but a reflection of the transformations occurring at every scale of existence. The guiding principles of my approach to understanding nature of time. In treating the topic of the nature of time with the ambitious to provide a complete description of the nature of time, with a clear, non-circular definition using a common-sense approach, that is without invoking highly technical concepts of the modern science and technology or entering subtle philosophical controversies, I have followed the following principles which need to be accepted to uphold the validity of my thesis. 1. Matter is real and fundamental. The reality of existence of matter as it appears to our senses have been contested by the philosophers and the physicists for centuries if not millennia. However, there is no clear victory with either side, whether the matter as appears to our senses is real or not. As one can imagine, even the concept of the real has been debated with inconclusive results. Despite these debates, our daily experiences offer a practical answer. For a simple man's mind who has not been prejudiced by those intellectual controversies, matter is real. It is real because when he is hungry, eating food can render him full. When he is thirsty, drinking water can quench his thirst. When he is hit by a stone on his head, he loses consciousness and feels great pain. While thinking about food, water, or stone cannot do much to him. So, my reality of matter is in this context. To me, the matter is real, because I can touch it, I can smell it, I can eat it, etc. 2. Motion is real and fundamental. Again, there has been controversy about the reality of motion for millennia. Some ancient thinkers like Parmenides and Zeno doubted whether motion was even possible. Their paradoxes puzzled generations. Yet others like Heraclitus believed that everything is always changing. As Aristotle mentions in Metaphysics, Plato was completely obsessed with this idea of Heraclitus regarding permanent flux, so much so that he thought everything in this world were unreal, as everything was changing continuously. Therefore, he philosophized the doctrine of realm of ideas, that is a realm where the real unchanging things exists and the things in this world were mere copies of those ideas. A simple man unprejudiced by the philosophical controversies would very well know that motion is real, such that he can move around himself. He can go to work, he can go visit his friends, etc. He can fall off a cliff and break his bones if he is lucky enough to survive. 3. Space is real and fundamental. Space is not any different from the matter in motion in terms of philosophical controversies. The most famous one is the one put forward by our good old friend Immanuel Kant. For him, space is not something like a container that exists independently out there, nor is it something we infer from experience. Instead, space is a pure form of intuitional structure of the human mind that organizes how we perceive the external world. However, from a common sense point of view, space is indeed out there. You could have a room with a small space or a room with a big space. You could remove everything, but the empty space can be still there. You could even remove the air, but the empty space as a vacuum can still be there. I do not want to get into the quantum physics understanding of vacuum, which could still have quantum fluctuations. 4. Causality is real and fundamental. Similarly, we are aware of the controversies about the concept of causality, especially those put forward by the Scottish philosopher David Hume. However, the philosophy of David Hume, to me at best, is confusing. We do not even know for sure on what ground he is rejecting the causality. Is it on the ontological ground or at an epistemological level? For an ordinary person, though, causality is obvious and very real, meaning that effects follow the causes necessarily, at least on the ontological level. Causality is the basis of all our physical knowledge, scientific laws, as well as our moral and ethics, justice, and religious teachings. Demystifying some of the difficulties about time. 1. Existence of things outside of time. One assertion that used to trouble me deeply was the notion of things existing beyond or outside time. How could such a possibility be conceived? If time is viewed as an omnipresent universal flow, how could there be entities beyond its reach? Similar to a fish immersed in the ocean, how could some continue living outside it? However, if time is merely the measurement of motion or change, simple entities, such as electrons, quarks, or positrons, which do not undergo internal change, can be considered timeless. Although these particles can move in space and be measured by an observer through time, they themselves do not experience time because they do not change. Thus, it becomes easier to understand that an electron, for example, exists outside time. Note that while electrons might theoretically decay into simpler particles, here I have considered it as fundamental, non-decayable units, for illustration purpose. 2. The smallest unit of time. If time is viewed as a continuous flow, it becomes impossible to pinpoint the smallest unit of time, because any chosen unit can always be divided in half, leading to an endlessly smaller unit. However, when time is considered as a measure of motion or change, defining the smallest unit of time becomes more feasible. By combining the smallest possible distance, that is the Planck's length, with the highest possible speed, the speed of light, we can define the smallest unit of time. This yields the Planck time, approximately 5.4 by 10 to the power of minus 44 seconds, which is the smallest time interval physicists can conceptualize. It is important to note that the existence of the smallest unit of time does not imply that it is fundamental. just as heat exists at the macro level but can be reduced to molecular or atomic motion at the micro level. 3. Is time travel possible? Time travel, while a captivating concept, presents significant challenges. Viewing time as the measurement and ordering of events within the universe based on causal laws, traveling to the past would necessitate reversing the sequence of all events and motions across all scales. In other words, time is not a local phenomenon that can be changed in one locality without affecting the rest of the universe. As such, time travel, if not impossible, would be extremely a rare phenomenon with practically zero probability. Purely, based on statistical laws, innumerable possibilities of changes and movements are open for the matter in the universe. Given the enormous number of possibilities, the probability of any given specific course of events in the future is practically zero. Therefore, moving into the past or traveling back in time would amount to the universe to follow a specific course of events in the future. Given the close to infinite number of possible courses of events open in the future, the probability of time travel, that is for the universe to follow a highly specific path among infinite possible paths, becomes zero, or in plain language, it is impossible. Furthermore, the human mind's capacity for imagination often clashes with the hard constraints imposed by the physical world. While our minds can readily conceive time travel, the reality of the universe, whether governed by fixed laws or governed by chance, may ultimately preclude such a possibility. This inherent conflict between the boundless imagination and the limitations of the physical world has led to intellectual tension and ongoing debate surrounding the feasibility of time travel for generations, including among the top scientists of the modern times. Interestingly, later, I noticed that this argument is the central theme of the statistical mechanics proposed by Ludwig Boltzmann and other pioneers of the thermodynamics in the 19th century, an effort to explain the second law of thermodynamics, or entropy. Notice that I said that the future is open with innumerable possibilities, which means that even though we could travel back in time, with extremely rare probability, we would have gone forward, not backward, and hence, that travel back in time will be effectively a future, not a past. Can we travel in the future? Is it possible, for example, to jump from today, August 2nd, 2025, to August 2nd, 2026, and witness what has happened to the world, to ourselves, our families, scientific and technological breakthroughs, social transformations, wars, revolutions, and more? In other words, can we predict future events beyond those governed by deterministic physical laws, like eclipses? Even in a deterministic universe, such a leap forward, that is, skipping a year or even a single day to accurately foresee these developments, seems implausible, given the involvement of an infinite number of interrelated factors or causes that shape any given outcomes or effects. This complexity makes it impossible to predict future events with reasonable confidence and presents a compelling argument against the feasibility of time travel. In a way, predicting the future resembles traveling back in time, as both involve imagining specific sequences of events. Yet, the realization of any particular chain of events, amidst infinite possibilities, is statistically so rare that its probability approaches zero, making such predictions or time jumps not just impractical, but fundamentally impossible. 4. Does time's trajectory have a definite pattern? It is curious to think that many people have notions about the shape of the trajectory of time. Some consider it as a line, others like a circle. However, if we consider time as a universal phenomenon which is the measurement of all motions and changes and the interaction of all those motions and changes in the universe, given the holistic nature of this measurement, one cannot have an independent frame of reference to draw a definite trajectory for time. Note that when we speak about any trajectory, we need a frame of reference. For example, something is linear compared to something else, such as a ruler or other trajectories. Something is circular compared to something else, for example the distance of its circumference from its center which, as per definition, should be equal at any given point of its circumference. Therefore, it is impossible to discern a clear pattern in the trajectory of a holistic measure like time. 5. Does serial time exist? Some people consider time as a sum of a series of moments like a line, which is the sum of a series of infinite number of points. In other words, a continuous stream of moments flowing independently of any physical processes. This notion of time is called serial time. This way of thinking about time is flawed because it considers time as an independent entity with its own specific units, a fundamental reality which could exist as a flow, independent of matter and change. As we saw earlier, the time measures the motion and change of matter. Therefore, without matter and change, we cannot speak meaningfully about time, neither its flow nor its units. Therefore, serial time, like the flow of time, is a mere illusion. 6. Does time have a beginning and an end? Essentially, this question pertains to the existence of matter and change, because without them, there would be nothing to measure with time, and thus there would be no time. I believe that matter and change have neither a beginning nor an end. The Big Bang and Big Crunch are merely minor events within the vast arena of what I would call the infinite cosmos. Therefore, contemplating the beginning or end of time is an absurd notion. In conclusion, if time emerges from matter and change, rather than being a fundamental aspect of the universe, our perception of its flow may simply be a mental construct. This view encourages us to reconsider time as an outcome of interactions and transformations of matter and energy. Your thoughts or questions on this perspective are welcome.